All right, so it is now 11:20. The first group that will be going is the drone package delivery system. So I welcome all the presenters to turn their cameras on or mute themselves. This project is advised by Dr. Edebegi, and like I said, it is the drone package delivery system by Sahad Ahmad, Joshua Anand Sai, Parker Revere, and Cedric Noel. So take it away, guys.
Hi guys. So for our senior project, we did the autonomous drone delivery system. My name is Saad.
Cedric.
I'm Josh. Cedric, are you sharing the screen? If you are, I can't see it.
Yeah. Do I have share rights?
You should. If you don't, let me know.
Okay. All right. Give me 2 seconds.
Good catch. Let's see that.
All right. You guys can all see that, right?
Yes.
Yeah.
Okay.
All right. So so for our senior project, we did the autonomous drone delivery system. My name is Saad.
I'm Josh.
I'm Cedric.
And I'm Parker.
So for the goal of our project, we basically want to develop a package delivery system for our TCNJ campus that would allow students to quickly receive small meal packages. And we want to do this in order to speed up the time that students and faculty receive these packages, and also do so in a hassle-free and convenient manner. So for the requirements of our project, we said that it should be able to carry these small packages to and from different buildings on campus. And when it does so, it should provide the user with a notification of when it has arrived and departed. It should have an app integration so that students and faculty can request to receive or send a package to and from their location. It should have around a 10-minute flight time to allow for return trips, and it should be able to fly a payload of about 5 pounds to fit the small packages. And for our drone specifications, we defined it to have an average flight time of around 10 minutes, a payload capacity of about 5 pounds, and an autonomous range of 1 mile.
So as far as our frame, we designed our frame originally in SolidWorks before we got all of our materials and had it cut. We were originally considering 2 options, polycarbonate and carbon fiber. The carbon fiber was the stronger option. However, we did decide to go with the polycarbonate because of cost. And then the next few slides will show our frame designed in SolidWorks. So this is the upper portion. We have pinholes on each of the 4 corners, which is where we're going to connect our arms. And the next slide will be the bottom part. Again, those pinholes on the corners are where we connect our arms, which will be shown in the next picture. And on this bottom part here, 1 slide back was where we're going to keep the package on the bottom. And then the next slide is the arm. The pinholes on that circular region are where we mount the motors. And then the 4 pinholes on the lower left side are where we connect each of the 4 arms to our main frame. We also ran a stress analysis. As you can see, there's a little bit of bend in the arms when we do get up to like full throttle with the motors. But according to the stress analysis, we decided that it wasn't going to affect the actual arms or cause any breaks because of the stress analysis.
So this is our projected weight for the final drone. So these are just all the parts that are and components that are going to be put onto the frame, as well as the frame itself, combined together, and then along with the payload, and that totaled a total of 13.46 pounds. And with the motors operating at full throttle, they are capable of lifting, I think, around 18 pounds. So this was well within our range of what we could accomplish. Next slide. So for our web app design, we used an SQLite database, and it's designed coding with Python and Django. And this is just a use case diagram of how what functionalities the user can have and the functionalities that the admin can have. So this is just a display of what our homepage is going to look like. The admins can log in through here, and when users would like to request a delivery, they can hit the request delivery button. And then this is the user request page where they can enter in their email address, enter in their name, and select a drop-off location from this list of drop-offs, and then submit it. And then the next page is the admin location where they can view all the requests. And this is just a Django admin page, and they can see all the requests that have been added from the user.
Okay, so moving on to the hardware portion of this project. So when we got all the parts, we did kind of like a basic functions check. So we tested the motors and ESCs, the speed controllers, and they all work as expected. We calibrated them with each other so that they'd all respond to the same throttle inputs, and that was successful. We tested the LiPo battery, and the battery charge and discharge worked properly. And then as for the flight controller, all the motors powered up and powered down as we expected. And then this is just kind of like a quick video of kind of what that looks like. So as you can see, that's pretty much just the motor throttling up and down, powered by the ESCs and the battery. And yeah. Oops. Okay, so for building the actual drone, this is kind of like the whole wiring schematic that we've been following for the drone. So as you can see, the ESCs 1, 2, 3, and 4. So these are the speed controllers that actually control the speed of each motor. So not shown in this diagram, the motors connect to those each respective ESCs, motors 1, 2, 3, and 4. And then in turn, the signal wires from the ESCs connect to the Arduino board. So, I mean, we just arbitrarily chose the pinouts here, but we used 4, 5, 6, and 7 for the input pins for the speed controllers. And then for the receiver, there's the throttle up, there's the roll, pitch, and yaw. And those were put into pins 8, 9, 10, and 11. The power, the VCCs can be seen going into the 5 volts. And then the MPU 6050, that's basically just our accelerometer and gyroscope so that the drone knows its orientation and we have some kind of auto leveling feature. So this week we actually attempted to test our drone flight. So we did an initial flight test. We had a brief airtime. However, the frame ended up failing. I think the screws were the primary failure point. They ended up shearing off and the frame fell apart. So to fix that, we're going to be purchasing replacement screws of a different material, ideally metal, and then test the flight again. We're going to perform another stress analysis and ensure improved strength, and then stabilize the arms to reduce flex. So I think as you saw in one of the previous slides, the arms flex a lot under tension. I think one of the reasons why that the screws fail is we didn't really account for the torsional forces that would be exerted from the motors onto those screws, which is kind of why they were a failure point.
So for our next steps, firstly, we have to repair the drone and retest the flight with our new screws and our improved arms, and hopefully get that up in the air and working. And then next, we're going to continue working on integrating the GPS module into the flight controller and get an autonomous flight going. And then we're also going to continue to document our testing protocol that we have made and make sure everything's satisfied, and document our safety analysis and make sure this thing is safe to fly in the air.
Okay, so I guess we have 5 minutes for questions. Anyone have any questions?
Yeah, I have a question. What do you have to do about the FCC? Is there anything you have to do in terms of compliance?
Oh yeah, Josh can actually answer that.
Yeah, so we had to get a certificate that we filled out, and we have it. And while we're flying it outdoors, there's an app, because we're right next to Trent Mercer Airport at TCNJ. We need to get permission to fly the drone at any time. So there's an app that you can check if you have permission to fly it at that time, and we need to fly that. And then the drone also has to be labeled with our certificate number.
Wow. Very good. Very important.
Mm-hmm. Any other questions?
How much time did it take to figure all of this out? It must have taken a lot of time.
Yeah,
Well,
so actually the flight controller itself was kind of like, I feel like, the most involved part, because we had to integrate, like the gyroscope, and then there was like a PID controller that we had to code, and that had to kind of work with like all the speed controllers and all the other hardware that we have. I mean, that was the majority of the last semester, and then this semester we're kind of just putting everything together and trying to get the automation coming.
We have a question about our majors. So I'm a computer engineering major. Cedric is electrical engineering, Saad is electrical engineering, and Parker is also electrical engineering majors. So ideally, this project would have liked a mechanical engineering major to work on the frame design and work on everything in SolidWorks. And if we had one of those with like more experience, the frame probably wouldn't have fallen apart. But that was definitely a learning curve that we had to do.
Great idea. Great idea. Fabulous.
Thank you.
Okay, any more questions, or am I free to take it over to the other group?
I'll give it one more minute, and then yeah, we can hand it over to the other group.
Oh yeah, so the question was in the chat, any particular firms or companies you guys are looking to work at in the future? So I'm actually an ROTC. When I graduate, I'm going to be commissioning into the Army as an Army officer. So that's pretty much what my career is going to be for the next couple of years. Parker, Josh, you guys want to?
I'm currently still searching and still applying and just waiting to hear back from whatever I can get. I don't have anything specific in mind necessarily.
Yeah, I don't have anything in particular. I'm also looking around.
And I am heading down to PSCG Nuclear to do systems engineering there.
That's great.
All right. It seems
That was
like
outstanding. That was outstanding. Thank you so much.
Thank you.
Thank you very much, guys.
Just
Great presentation.
Great job. Just a great job.
Thank you so much.
Thank you.
Thank you.
All right, so I'm going to hand things off. Just get right into the next group. The next group is the teleoperation of humanoid robot via exoskeleton control scheme, advised by Dr. Kim. So I invite those presenters to, yep, they're already here. So this project is by Jordan Sinaway and Brian Dawson. So take it ahead, guys.
Thank you.
All right, thank you.
So today, as mentioned, we will be presenting on our project, which is the teleoperation of humanoid robot via exoskeleton control scheme. My name is Jordan Sinaway. I'm a computer engineering major.
And my name is Brian Dawson. I'm also a computer engineering major.
And our advisor is Dr. Kim.
So just going to quickly go over the agenda. We're going to start with our introduction, then go into the project details, finish with a summary, and then we have some time for questions.
So just the general description of our project is we focused on developing a solution that utilizes an upper body exoskeleton to control a humanoid robot. And this solution uses potentiometers that capture joint ankle positions. And then the potentiometers are read by ADCs, which are from a connected microcontroller. And then the microcontroller applies mapping, smoothing, and acceleration and deceleration algorithms to this data. This data is then sent over a serial connection to a PC, which is running a Python intermediary layer, which takes in the data and translates it to robotic commands, which are then passed to a now robot, which is a small scale humanoid robot. And then this all happens in roughly 60 or 70 milliseconds. So it copies the user's movements in near real time.
So just quick background, robotic teleoperation is the remote operation of a robot. It has uses in hazard waste disposal, surgery, and nuclear reactor maintenance. Current control systems are expensive and often proprietary. They have suboptimal latency, and we found them to be unintuitive. So our proposed solution is using lower cost components, open source coding, improved latency, as Jordan mentioned, and natural and intuitive controls. And so here's a little bit more background on the now. As Jordan mentioned, it's a small humanoid robot. It has 21 degrees of motion and is fairly good at mimicking the human joints due to the fact that its joints are similar to the human. There's several sensors, and then you can connect it to a computer via network, and then you can control it using the proprietary choreograph software, or in our case, we use the NowQI software development kit. And then here are design specifications and deliverables. Our total system weight is required to be under 20 pounds, though at the beginning we estimated to be under 10 pounds. Latency is, we would like to be under 150 milliseconds, joint accuracy to be within 3 degrees, slight user encumbrance, and power consumption of under 120 milliamps. And our deliverables are to have a prototype, a hardware prototype with all the software and the successful control of at least one arm. And then here's a quick overview of our architecture. On the left, you have the exoskeleton, which contains the power circuitry for the potentiometers and the microcontroller. And then those potentiometers, as Jordan mentioned, send their data via ADC inputs to the microcontroller. This then translates the data and sends it via serial bus to the Python layer, which will then further translate it and send via the NowQI SDK. The commands will then be sent over Wi-Fi to the robot.
So here is just the general exoskeleton concept that we came up with about 2 years ago, just to try to, when we were conceiving of this design. On the right, you can see the degrees of freedom and general movements of the human arm. And on the right, we kind of just did a basic sketch just to try to design something that would be able to copy and translate these movements as an operator was wearing it. So as part of this whole design, we need to, as I mentioned, we need to use joint angle sensors. So we had to decide between a few joint angle sensors and decide which one is the best suited to our application. The main ones we considered were potentiometers, mechanical rotary encoders, and magnetic rotary encoders. Overall, potentiometers proved to be the best solution given our total amount of money we had, as well as the certain situation in which we're using them. So mainly because they provide the best possible resolution given the 13-bit analog to digital converter, or ADC, that's part of the microcontroller. So it provides a resolution of 8192, and that's compared to mechanical rotary encoder, which only has 36 pulses per revolution, which is equivalent to 1 pulse per 10 degrees. So that's not as fine a resolution as we're looking for. In actuality, the magnetic rotary encoders on the right side of the table would actually be the best option because they are the most accurate overall and don't have any mechanical moving components. However, their price was kind of defeated the purpose because the total cost for just the sensors would have been greater than our total budget of $250. So we ended up in the end going with our potentiometers. And the potentiometers that we selected were the Born's PDF 241 S425F, and they're rated for 1 million shaft revolutions. So they should more than hold up to the number of revolutions and movements that we have for our system. So I bet you're wondering now what it actually looks like. This is what it looks like. This is our CAD model. On the left, you can see the back mount, and on the right, you can see the full design with all of the subjoints and components. And where the potentiometers are placed on a given arm. Now, this is a closer look at the elbow joint design. It's using what I designed or called forks and it's using a kind of universal joint type approach with a central axle and two moving components on either side. And you can see the axes of rotation here. So this is what the elbow joint looks like. This is what the wrist joint looks like. It's using kind of like a joystick type approach where the user would be holding this component and moving it around as they want to move the robot's arm. And then here is the shoulder joint, which shows how the potentiometers kind of slot in to the holes shown on the other components and fit together and are able to kind of measure the axes of rotation as the joint is moving. Here is the architecture of the electronics. It's fairly simple. On the left here, you can see just the 12 potentiometers we used for the upper body exoskeleton. On the right is the microcontroller, and the bottom section here is just the power delivery circuitry and some other passive components. So to facilitate our design and kind of quick prototyping, we developed a printed circuit board, or PCB, to speed up the testing and overall development. This PCB integrates a microcontroller, potentiometers, and the power system, and it kind of serves to reduce the wiring complexity and difficulty and kind of makes it all nice and neat and easier to work with. So this is what you're seeing on the bottom here is actually our second revision, which incorporates these new connectors, these white connectors here, because they actually we had a different sort of connector, but it was actually prone to mechanical failure due to the stresses placed on the system by moving. So we had to transition to new devices, and this serves the purpose that we need. So it's pretty good.
So for the development of the embedded code, it takes the analog sensor data is read in via the ADC and converted to a digital data. It has a range of 8,192 or 13 bits. Then we apply smoothing and mapping filters, and then the data is sent via a serial connection to the Python intermediary layer. You can see sort of what that looks like, and that's the serial data from all the potentiometers being sent out. So for the intermediary Python layer, this is a Python script that first it connects to the robot, does some error checking with this connection. It sets up commands to ensure proper movement, ensures that the joints are working properly. Then it creates a function for translating the serial data into usable robotic commands. Then it creates that serial connection to the microcontroller with some more error checking. It takes in and segments the serial data for each joint, and then creates a thread for each robotic movement. This ensures that they can occur simultaneously and keeps the latency down low and has a little bit more error checking.
So here you can see the components once they've been manufactured, because we designed them in CAD, then had them printed out on some of the school's industrial 3D printers. So you can see how everything kind of comes together here and how everything slots in. On the left is the back mount. On the right is the shoulder, one of the shoulder joints. On the left here is one of the elbow joints, and then on the right here is one of the wrist joints. So, and then here I am wearing it. You can kind of see how it goes on the outside of the user's body. And it's kind of unintrusive and pretty intuitive to use. So we didn't want to have something that was strapped to the body and restricted the user's movements. And here's just the back view, and it shows me kind of just holding it up, and so you can see the full design here.
And so for the testing of the exoskeleton, we first assembled the left arm, and then we wired the potentiometers and did some testing. We tested to ensure that all the data was being processed and transmitted correctly. Fortunately, during that time, we had problem with the now that we were using that forced us to use the right arm during testing. And we were able to figure out that data was being transmitted correctly, but that we needed to make some changes to the exoskeleton mechanics and the code to more accurately map the full range of motion of the operator. And then after that, we finished assembly of the right arm so that the full construction was complete. And then we did some more testing to ensure that everything was being done correctly. We were able to test both arms at the same time with a new Now robot. We figured out that the data is being transmitted more or less, is being transmitted correctly, and that the robot is copying the user's movement more or less accurately. And we do have some improvements that need to be made, but we're going to show you next a video sort of at our current stage.
And as Brian mentioned, here is a demonstration video. It's fairly quick, but it kind of just shows the general capabilities of the exoskeleton, and that the movements are being mapped in near real time. There's still a little bit of some angle offset problems and some I guess some general flexibility things that need to be changed. But overall, it's still fairly good, and we're progressing along pretty well. All right.
So sort of summary and conclusion, we successfully developed a working prototype of the upper body exoskeleton, and we're measuring the movements of the left and right arms of the operator. And we designed and developed all of our components, and we more or less completed our deliverables. As I mentioned before, we have our requirements, and our total system weight was actually much less than we expected, 4 pounds. Our latency is very good. It's around 90 milliseconds. Fortunately, as we mentioned, we're still working on joint accuracy. It's about 7 degrees instead of the 3 degrees. Our user encumbrance is good, as it's slight, and the power consumption is even less than we expected at 85 milliamps.
And that about wraps it up. Thank you for listening, and now time for questions, if any.
Yeah, we have a few minutes for questions. If you have a question, feel free to put it in the chat or unmute yourself to ask. Dr. Kim approves. Yeah, I actually have a question.
Sure. Yeah.
When you guys are showing your demonstration video, you mentioned that you have still have some angle issues to get the proper adjustments to respond.
Mm-hmm.
Do you guys have any thoughts on how you're going to address that in the future?
Sure. Yeah, I can answer that quickly. Basically there's because the way that we set up the joints isn't perfectly analogous to how the human body works slightly differently than the now works, because it was made as an approximation. So we can actually just add angle offsets, plus or minus a certain number of degrees to certain joints, and that'll help adjust it. There's also some built-in anti-collision underlying software in the now. So if you try to raise the arm and have it hit itself in the head, it won't do that. So there's almost like a sphere of area that it can't go around parts of the body. So that kind of offsets some of our angle measurements a little bit. So we're trying to work around that and get some offsets to make sure it's working correctly.
Awesome. Hope that works out for you guys.
Yeah, thanks.
If we have no other questions here, I think we're free to move on to the next presentation. Thank you, Jordan and Brian. Great presentation.
Yeah, I had a question.
Go ahead.
So obviously this is designed to be controlling an external robot, correct?
That's correct, yes.
Have you given any thought to actually human exoskeletons to assist people who are disabled?
I mean, I certainly have thought about it, but it's almost a whole nother realm, because it's there's a lot of medical considerations and stuff that you have to make sure it's not actually harming anybody as part of the design.
Right.
And it's quite difficult to have something that's both efficient and wearable. It's something we ran into with designing something that had no motors at all and had nothing like that. But if we add motors to it, it's
Okay.
a lot more
curious. I was
Yeah.
at a conference about 7 years ago, and I saw a lower body exoskeleton, and a guy who was a paraplegic basically put it on and got up and walked. Of course, he had a cart full of batteries behind him. But my wife has MS, so I'm kind of interested in the human exoskeleton projects that are going on. So
Yeah, it's definitely a great field, and I hope to kind of work on some of that someday.
I mean, are there companies who are actually? I've heard there are companies that are actually producing them now, and they were talking about like a soft exoskeleton. So
To my knowledge, there are some soft exoskeletons and exoskeletons. I think Stryker is one company that develops them, but I don't know too much about that area.
Okay, I was just curious. Since you're well versed in this, you might have known. Sorry.
Thank you.
All right. If there are no further questions, I invite the next group to present. The next group up is Electric Excursion, advised by Dr. Katz and done by Keith Garcia and Nick DePaulis. I'm not sure if I'm saying that right.
DePaulis. It's close enough.
Thank you.
You're welcome.
So go ahead, guys.
Okay. I'm Nick DePaulis.
Keith Garcia, and we are the Electric Excursion team. This is just an abstract of our design. So personal transport vehicles are emerging through college campuses and urban areas. These vehicles are used for both recreation and commutation, provided by a clean, simple propulsion. We chose a longboard because of the storage and weight advantages, as well as the ability to modify individual components, which allows us to have increased customization. Our approach also allows for the opportunity to increase efficiency and accessibility to non-enthusiasts. So this is our quick introduction. As I said before, the use of small-scale transport is increasing. This is mainly shown through scooters, skateboards, and bicycles. These highlight the efficiency, but we aim to increase the usability and consistency of our design through the introduction of our electric assistive components.
So I'm actually responsible in this project for the mechanical, electrical design, theoretical analysis, the actual construction, and some preliminary testing, along with the safety research and safety applications that we're going to have to look at.
And I am responsible for the research and design, the VESC testing and analysis, the safety integration and analysis, and the after action analysis, which is the field testing. So this is just going over the background of our of this semester. So our goals are to test the prototype. This will be done through a control testing, which with a stationary model, and then a field testing, which is our actual constructed design. We aim to test and refine the speed and acceleration curves over various surface compositions. And of course, this is going to be performed with the proper personal protective equipment. And then we aim to incorporate and test safety features such as like a hazard detector. This will allow accurate detection and notification within a couple of feet. And after each test, we are going to verify the system integrity. This is just to make sure everything is within spec and it should be functioning as it should. Now moving on to the specifications, we aim to just hit 12 to 20 miles an hour, climb a hill of 10% gradient, which we see on campus, and have an effective range of 10 miles, which is approximately 5 times around the circumference of campus, and have a short recharge time of under 5 hours to be used on the daily.
So here we have our design specifications in more of a tabular format. The actual performance of some of these fields is still to be determined. This table will get filled with the data as the team continues to test the machine. And then here we have the list of materials and the place of purchase that we got them from. And then a continuation of that slide is the cost and order total and the actual order index. So it makes it a lot easier to read. And then it actually showed and aided us in our proposal for a budget increase. So here I can actually touch on that with our graphical representation of the progression of our monetary budget over the course of the project. We initially were allotted $200, but we required a substantial increase to cover our additional costs of materials. We requested and were approved an increase, and we're currently sitting around $682.
This is showing our labor budget over the past 2 semesters starting in August, and it is accurate as of March 17th, 2021. So this is just going over the VESC software. The software being used is called VESC VESC project. This stands for Better Electronic Speed Controller Project. It is compatible with many different ESCs or electronic speed controllers and allows for high levels of configurability with relative ease. Some additional features like the tutorial wizard will get users up to speed quickly and learning how to use the different tools that are at our disposal. It allows us to parse and display real-time data taken directly from the controller and convey the data onto plots. Another aspect was the ability to file and save multiple configurations to upload profiles to the board, such as beginner, intermediate, and expert levels.
So as Keith touched on before, the wizards pretty much allow for a more thorough understanding, and they reinforce the tools that are at the user's disposal. The VESC tool also has various fields for battery compatibility, current calculations to better guide the user and create boundaries unique to each user setup. In our case, for let's say our remote control, we were able to pair and tune our pulse position modulation remote control without having to have the motor spin up every time. And then when we got our configuration where we wanted it to be, we had the option to enable the motor, and then we could see in real time how our modifications affected the behavior right then and there. And then again, just as Keith touched on, with the processing of the real-time data, we're able to analyze specific aspects, such as, let's say, current draw relative to motor RPM. And this tool allows us to create more of a threshold to give us more control over our experience and then what we would like to see or get out of our vehicle. But one thing that was kind of a learning curve was that it does take some time to get used to the tool. It's kind of not as straightforward as some might think, but it is a valuable asset in a project such as ours. And then just to give you a little example of what that actually looks like. So this is what the tuning and mapping screen looks like for our specific PPM remote control. So here's the screen where you can change the different pulse lengths. In our case, when we received our remote, it could not reach 100% throttle, even when we would fully depress the toggle switch. And to fix this, we were actually able to reset our remote and then manually center our remote to behave as intended. And then in this one, you can see it's around 23%. Well, that was when I was around pushing it like a quarter of the way forward. So it's close enough considering I was just checking it with the naked eye.
This is showing our road to success from past to future. If you look in the top right, this is showing our preliminary design with the power button and the ESC in the standby position. Next is covering our stationary board design. And this was just mounting the rear truck with the motor, wheel pulley, and motor pulley. And it's attached by the belt. As you can see, that's in between the motor, which is on the left, and the wheel, which is the green part on the bottom right. And that leads us into our current design, which we'll be using for our field testing. And we're going to add grip tape to the top of the board to make sure the user does not slip off when they actually ride it.
So here on this slide is a rough mock-up and layout of how our first version of the test fixture, which you saw on the top right of the road to success, would look like. This is for use with a 40 amp power supply. We just had one of these on hand and we designed this test fixture around that. Then on this slide, it's the mock-up and layout of the second version. The only difference between version 1 and version 2, as you probably have noticed, is that this one has the power supply replaced with the 2 battery lithium-ion modules.
This is our first test fixture. In the bottom, under the drill, you can see a piece of wood that's clamped to the board. It's drawn up on to countersink holes, and that's what we'll be using to attach our motor to. And this was just to make sure when we were attaching the motor and running the motor that it doesn't physically crack the mount itself. So we'll have accurate data from that. And this is the motor attached to the mount, which will be affixed to the base.
Just like he said, here it is. The motor is mounted to the base, and then on the top right, that's where the power switch would go. And then on this one, we used a T-square, kind of just give us an estimate of where we would have to mount our speed controller board itself so that the cables from the motor could reach the speed controller, and also the cables from the switch were able to connect to the power rails of the control board. And then here's an image of me soldering some XT60 connectors onto the power switch module.
And these are the hoops that just needed to be crimped and then soldered. So this is a top view of our soldering station on top of our test fixture. On the left, you can see is the power button, and in the middle, you see the ESC with the XT60 connectors. This is one of our first designs, as Nick showed you in one of the preliminary designs, is the power supply is in the top left corner, and that's our in-house power supply. And there's our ESC and our power button, and nothing's on right now, which means that it's completely powered off and there's no power running through the ESC. This is just showing the standby position. It's highlighted in blue. This just means that it's awaiting instructions from the handheld controller, and upon these instructions, the light will switch to a green.
In this image, the motor bracket needed to be adjusted because during our acceleration and braking test, this is more for the stationary board testing, the belt was actually slipping off. This is due to our belt tension not being high enough, and also it's not exactly aligned perfectly, so like straight. So we actually added some washers in between the wheel pulley to get that alignment better and then reduce the chance of it slipping. And then in this image, this is more of like a side view underbelly of the board with the wheel pulley and belt being more of the emphasis there. The speed controller and other electronics are inside the protective cover shown to the top right. That's going to protect the batteries and the sensitive electronics so that if you hit something, it's not going to just destroy the board instantly. And then in this image is more of a top-down view with like a rider. The main goal of this was more to get a feel of how the board balances and to ensure that there was no bending or flexing, which would cause an issue with the underbody protective case and the motor. The team found that the board did not bend under the weight, and there was still like a substantial clearance between the case and the ground if a hazard such as, let's say, a stone or you go on some uneven ground would present itself during a commute. The top surface will be covered in grip tape, just like Keith mentioned, in the final stages of the design. And then, as with most learning experiences, there are some things we felt we would do differently if we had to do it all over again. One of the major aspects that we wanted to have more of was a great level of customization with respect to hardware. The current design that we have utilizes polyurethane wheels, which are good for concrete and smooth terrain, but we would have liked to implement some sort of off-road wheels as well to see how our system would handle itself in a more difficult and diverse environment. And another aspect we would also like to change would be a selection of a different remote control and electronic speed controller module. We would have liked to have been able to choose a remote that would have supported a battery level indicator and a possible display to have almost like a speedometer's function to convey more data to the user on the fly. And then on this, it's just a quick video showing the acceleration and braking functionality. Okay, any questions?
So we have about a few minutes for questions here. Feel free to unmute or put your question in the chat. I actually have a question.
Yep.
So you showed a picture of I'm guessing one of you two riding it before. Is it designed to be used as like transportation, or is it like could it also be used as like moving stuff from place to place, like things that aren't too heavy?
I wouldn't necessarily have it as unmanned because you can't really steer it unless you're on it. So I would advise against that. But I mean, theoretically, you could do that. but we haven't really considered that. It's more meant to be like something that would get you from, let's say, class to class, not necessarily a transportation vehicle, like with cargo.
Okay, got it. Thank you.
Thank you.
What was the most challenging part of the project so far?
The most challenging part was probably sourcing all of the components and making sure they're all compatible. They weren't all purchased from, let's say, one vendor, so they weren't designed to necessarily go together. So we more or less had to spec it out, as I would say. So you're like, hey, we're looking for a motor that's going to have a certain amount of torque relative to a voltage you're going to apply to it with the RPM. And that was kind of the most difficult, was learning about these vehicles, because I don't really have much experience in the field of, let's say, motor vehicles, like RC stuff. So the most difficult for me was honestly kind of getting a grasp on all of the aspects that come into this, because it's a control aspect, a mechanical aspect. You have all these different fields kind of coming together.
It certainly looks incredibly complex. That's all. What was the most interesting part of the process for each of you? What did you find most interesting in terms of your learning?
For me? Oh, go ahead, Steve. Sorry.
Yeah, I'll just start out. I think the most interesting part was definitely the research behind it, because there's many different vehicles and there's many different configurations, especially in terms of the motors, whether it's in the wheel, or we used specifically a belt drive, which was the most efficient. And in terms of the budget as well, because we were limited to a budget, we planned on putting 2 motors, but we ended up only using 1. So it's kind of interesting just to see, as Nick even said before, figuring out which components went together. It was quite interesting seeing how we can create an actual board that would be able to move each of us with the current budget that we were in.
Mm.
I kind of felt the most interesting part was kind of the experience of learning something new and taking an idea and making it into an actual object, like an actual product. That was kind of the most interesting and exciting thing for me. Was most of our classes are like based in theory. Not, you might get a few lab classes where you actually do something, but to have the ability to choose your own project and kind of walk it through its like life cycle, that's been pretty rewarding in my eyes.
Terrific. And the takeaways that that you have from the project in terms of how this will impact what you do in the future? Did it solidify what you're planning to do in the future or impact that?
So I'm mainly going to be going into like a graduate study with an emphasis, I'd like to be with an emphasis on power electronics and communication systems. So this project was more or less, you know, I have to map everything out, look at how these systems interact with each other, and also the communication from the remote to the actual controller. That was using a 2.45 gigahertz frequency, but which is, I believe it's not actually that, it's not restricted by the FCC for like these small applications, because it's not going to interfere with other devices. But the takeaway for me was more or less that it was kind of more of a learning experience for me. Like you're always learning, so I kind of enjoyed doing that, and I don't think it really necessarily affected it, but more or less reinforced like my interest in this area of study.
Great, good. Any other comments that you want to share with the audience and in terms of your learnings and how it has impacted you doing this?
Honestly, a lot of it is mostly research. So you always gotta never go into it blind. You always want to just spend your time and do the legwork before you commit to anything. Because if we just committed, oh, this product is highly rated and purchased it, we would have been stuck a long time ago. Research is key.
Great. Great project. Great project.
Thank you. Thank you.
Yeah. I must say, most of it went way above my head, but I really enjoyed it.
Yeah, thank you guys for presenting.
Thank you for your time.
Yeah, thank you.
Thank you all for
Um,
coming.
Great project. That was the last of the 3 senior projects. We will be starting up again at around 12:25. So yeah, your time is yours.
Thank you so much. Our next speaker is here, and we want to thank everybody who was here for the students' senior presentations. That was fabulous, and we look forward to our next speaker.
Hello,
Roger,
Karen.
thank you.
Rajesh here. Can you
I
hear
did-
me?
Yes, beautifully. I just can't pronounce your name well, so